Okay, so let's talk about 6.2, which is thinking of area as an accumulation or the integral as an accumulation. So not specifically just area under a curve. All right, so there's a few distinctions. So the first thing that I want you to notice that's actually important is that if we have an integral, keep in mind that means that little f is the derivative, okay? So when we integrate, they're saying that you're going to equal big F. So big F is the original function. Now, we haven't seen this idea before, but this is used a lot in calculus. So if you use the uppercase f, that's the original function, and this lowercase f is the derivative. Notice there is no f prime on that, but you need to know by the notation what the original is and what the derivative is, okay? So it seems really simple, but I don't think it's obvious. So if you miss that idea, that's common and it happens, but try to make that connection. The second thing is typically we think of f of x, but because we're going to start to move into applications, we want to start to think of x as time. And we saw this with derivatives. Now we kind of call these dummy variables. X doesn't matter, t doesn't matter. This could be the same thing as f of b if we want. So I call them dummy variables. Don't get bogged down by t and x. They all mean the same thing, okay? All right. So to make this easier, what we want to think of, since this is little f, I always like to write what my graph is in my own head so I remember, okay? So in my head, I would say, oh, that's a derivative, and I would write it on my paper. And so because this is a derivative, what they actually graphed are rates of change. Notice this is not a graph of the original function, okay? So we're going to start connecting those same rules that we had for function analysis when we were given the graph of the derivative to the original, all right? So we can think of, just as a context, think of little f as the rate of snow accumulation over an 8-hour period of time, all right? Because it goes from 0 to 8. So for instance, these are some words you would use to describe it if they asked. So at t equals 1, here we are, and they say, oh, snow is falling at the rate of 3 inches per hour. Now, falling you typically think of as negative, but that's not what this is implying. If this is snow accumulation, I mean, snow needs to be doing something. You could say snow is gathering. It doesn't matter. But snow is falling at 3. Notice the 3 is positive and the rate is inches per hour because this is a derivative. It's not just there's 3 inches of snow. That's not what this graph means. At t equals 3, right here, well, our derivative value is 0. That doesn't mean that there's no snow. It means that there is not snowing, okay? At t equals 4, our derivative value is negative, and so they're saying, oh, snow is melting. Melting is the best word. You don't want to say like you're shoveling and removing it, but if that was the context, those are some words you might use, okay? Notice we don't say melting at -4, or we don't say falling at -4 inches. That's per hour. That doesn't make sense when you talk, all right? So big F represents the total accumulation of snow at any point in time x. All right, so let's do some table values. So sometimes they might give you a graph and they define your integral. What I want you to notice is that they're saying that our start value is 0. And this makes sense with an application because that's usually when time happens. Now, you can have negative time because if this was like midnight, negative time would be before midnight. So don't think, oh, well, time can't ever be negative. Yeah, it can. It just depends on the context. So if we want to fill this out, and let's just say you wouldn't do a whole table on an AP exam or on my test, I would just ask for one specific value, but I'm going to show you how to do all of them. And then we're going to kind of interpret the meaning because together they mean something different as well. So on the first one, we know that these are x values. So what I'm really doing is we've got 0 to now x is 0 of little f. And so from our rules, well, 0 to 0, I didn't go anywhere. My next one would be 0 to 1. So from 0 to 1, to evaluate that integral, we want to use signed areas to evaluate integrals. Okay, so you can think of this two ways. I can split it up into a square and a triangle, or I could do it as a trapezoid. I'm going to write the formula for a trapezoid because sometimes it's just quicker. Base 1 plus base 2. Remember, the height, this would be my height, and my bases would be the parallel sides. Okay, so if I did a trapezoid formula, this height would be 1. My first base is also 1, and my other base is 1, 2, 3. Now, you don't have to do a trapezoid. You can find this integral any way you want. So if you want to split it up, please go ahead and do that. So half of 4 is 2. And it's above the axis. We went forward, so I know that that's my answer. I'm going to erase some of this. Okay. As I do these, I like to go ahead and write my values up there because we're going to kind of use this later. All right, so if we do 2, well, that's looking from 0 to 2. So this area, 1, 2, 3. And so I would add these up. At 3, that's a triangle, so 1/2 my base times our height, 3. So half of 3 is 1.5, so 6.5, because we went from 0 to 3. This one, 0 to 4. So notice this is negative because we're under the x-axis, and it's still a triangle. 1/2 base times height, 1, 2, 3, 4. So 2, negative 2. This one's the same. So what do we got? So we had 6.5 and we want to subtract 2. At 5, this is also negative 2. 6 goes from 0 to 6. So let's see, another triangle. 1/2 base times height, so 0.5. So I'm going to add 0.5. Then we stopped here, and typically we will wherever it crosses the graph crosses the axis. So at 6.5, you can assume that that's in the middle, even if you weren't told. If we use slope, we would be able to find it as well. But 1/2, our base is 1/2 times our height is 1. So 1/4. So I'm going to write 0.25. So if I add 0.25, this one's the same triangle, but this is going to be negative 0.25. So I'm going to take that off. And then that's 1, but it's negative. So we end up at 2 if I go from 0 to 8, if we'd add all those numbers up. Okay. So you could find some individual values, integral values, if we define it this way. All right, let's talk about another concept. And we'll do more with this one later as well. But let's say we think of this idea, because this is a big concept here that we've never really done. So this is saying if we could cover this up, so I'm going to ignore this, okay? What happens if we take the integral of little f? Okay, well, if I integrate little f, I'm going to write it over here, we get big F. All right? But that's not the question. This was still there. So I'm going to take this off. And this is saying, well, what if we have the derivative of big F? Well, the derivative of big F is f prime, which we also defined to be little f. And so that's what this whole thing is saying. If we take the derivative of the integral, because these are inverse operations, we're just going to be left with the inside. And so some people say, well, why do we change it from f of t to f of x? Just to show that we have done a process. Remember, they are the same though, but we changed the variable just to show that we have applied a concept, okay? You would not be marked wrong if you didn't do that, just so you know. All right, so since big F is equal to the integral, then I just showed that these two are true. Okay, please use proper notation and capitalization because it is going to make a big difference now. Never say it, never say the function, always name it properly. Okay? All right, so keeping that in mind, what we want to do is find these values. So if I want big F prime, if I took the derivative of the integral, well, big F prime is the same as f of x, little f. Okay, these are the same. So when I want to use 0, it's really saying, hey, what's f of 0? And little f, remember, oops, is our graph. So I'm looking at what the function value is that's graphed. So at 0, our function value is 1. We're not accumulating anything here. This is f of 1, which is 3. F of 2, and you can see how this is going, 3. F of 3 is 0. F of 4 is negative 4. F of 5, F of 6, 6.5, F of 7, and F of 8. Okay? So this described our original y values of f. This one describes our derivative f prime values. Okay? They're very different answers, very different ideas. So now once we know what our original values are and what our derivative values are, we can use some of that curve analysis and the rules that we did before to analyze, well, what happens on our original. So we can find when our original function increases, we can find extrema, we can make sign charts, we can find concavity, everything else. And that's what we're going to be looking for. So let's talk about concavity before we do this example. So if we want concavity, we want f prime. So remember, f is the original. F prime or little f is the derivative. So f double prime, which if I take the derivative of that, I take the derivative of little f, is the second derivative for concavity. So to find little f prime, we're going to be looking at our tangent slopes to this graph, okay? That would give us f double prime. So I'm going to make a little note here. So what they want us to do is they want us to sketch a graph of f. So remember our rules. I'm going to use some analysis for increasing and decreasing, and we actually have specific y values. So let's go ahead and plot these right here because those are the original y values. So I've got 0, 2, 1, I'm sorry, already 0, 0, 1, 2, 2, 5, 3 at 6.5, 4 is at 4.5, 5 is at 2.5, 6 is at 3, 3.25, back at 3, and then at 2. Now, this is the original graph. Before you guys had a shape, but we didn't know the original values unless it was given. And now that we know integrals, everybody should have identical graphs, okay? So that's all using the integral values. Now, if we didn't know those, we can make a sign chart. So I'm going to put it over here. And so I'm going to say f, which is really f prime. And so that's what we want to look at. So remember, the rule was when our derivative was above the axis, our graph was increasing. So we're going to be increasing till 3. So I'm going to go down here to 3, and I'm going to say increasing. We're decreasing till 5. We are increasing until 6.5. And then we decrease. But look at our y values. Because we know our y values, that pattern is actually already prevalent. So there really is no need to make a sign chart if we have done our integral values. So let's go ahead and talk about concavity. Big F, which is little f prime. So I'm going to use blue. So I need to go up here and let's look at our slopes. So the tangent slopes are positive until we get to 1. So that means on our second derivative, we're going to go, this was at 0, this was at 1. We're positive, so concave up. So I do it right here. So I just say, oh, concave up. I make a little note. Then I have a 0, so that's no concavity. And that happened till 2, so none. Then we have negative, 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 all the way until we got to 4. So if I made a sign chart, this is what I would do. So concave down. So I'm going to say none. So then concave down, concave down. All right, so then after 4, we're up, up, positive, 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 positive until 6. So then at 6, we'll say positive, concave up. So up, up. Then down all the way until 7, and then none. So negative, 0, so none, and then concave down. So concave down and then none, which means it's a straight. Okay. So then we're going to apply this. So try to exaggerate it if you can. So concave up. We have none, which means it's a straight line. Concave down, down. So we're going to curve down. Then concave up, up. And it kind of follows, but you want to make sure that you have that concavity. Concave down, and then we have none, so we're going to have a line. Okay? And so honestly, all students should have that same graph. In the same spot, everything identical now that we know integrals. Okay? So we can use our function analysis, our integrals, to make a graph of the original. And so we could find max, min, we could describe intervals, things like that. Sign charts are good to show things, but remember you would want to use words. All right, so let's try this next example. There's a lot of questions here, but they are related. So first, same idea, they do this a lot now. Our original function is f because little f is our derivative. So I always like to make a note of that. They do tell you it's a semicircle, and we're going to use the geometry. So this is going to combine 6-1 as well. So notice we start here. So all of those rules now, because we do have some negative x values, if we go backwards, remember it's the opposite sign, okay? And we use signed areas. To help evaluate. So f of 0, you don't have to show this work, but that means I'm going to plug in 0 to 0 of little f. And so we're not going anywhere. F of 2 is really 0 to 2. So 0 to 2, that's a quarter circle. So 1/4 pi r squared. Our radius is 2, so 2 squared is 4. 1/4 of 4 is 1 pi. There we go. It's above the axis and we went forward. F of 4 is from 0 to 4. And so if that's pi, this is also pi. F of 6, so 1/2. Our base is 2. Our height is 2. So 4, half of 4 is 2, and so that's -2. So f of 6 went from 0 to 6. Notice I don't have to write it now. So I'm going to add those together. So 2 pi. Oops, I forgot my 2 there. And then take off the 2. You would leave your answer like that. Don't get a decimal. Okay, these would be no calculator questions. And this could be on the free response as well as multiple choice. Okay, but you wouldn't be answering all of these questions, just so you know. You would pick one of them. All right, my next row, f of -1. So keep in mind, this means I still start at 0 and I go to -1. So you need to notice that you are going backwards. So that's automatically going to be the opposite sign. So if I do this, I get 1/2 base times height, which is 1. And then because I'm going to put 1 for my area up here, but because I know I'm going backwards, my answer is -1. Okay, I like to keep the areas, I don't know. I just like to keep them positive. I don't know why, but I do apply rules. Same thing here, 0 to -2. So I know this is also 2 more. So I'm going backwards. So 1 and 2 is 3, and we went backwards. F of -3, well, these two are going to cancel out. I don't know what they are, but I know if that's a positive and that's a negative, even if they're opposites, they're still the same amount of area. So I'm still going to get -3. And so f of -4, those cancel. I never even find them. And so I've got 1/2 base times height. So I get 1, and I'm going backwards. So this is really -3. Those cancel. And then I want to do +1. So I get -2. Okay, so I do apply the opposites. All right, f prime of 4. Remember, if this is f is my original big F, then f prime is really little f. So on a free response, I would actually even write that connection so the reader knows that you know what you're looking for. So f of 4 is what I see, 1, 2, 3, 4, and that function value is 0. So this is little f. So at 2, my y value is 2. F of 6. So at 6, we're at -2. And that is f of 5, -1. Okay? Now, double big F prime, well, that's the derivative of its derivative, which little f is the derivative. So I want little f prime of 2. So that means I need to find the tangent slope. So I'm going to go to 2. And if I drew my tangent slope, since that's a max, it would be horizontal. So our tangent slope is 0. This one is little f prime of 5. So I go to 5, and I want to find this slope. So rise over run. So rise over run. So -1 over 1 is -1. At -0.5, here we go. Okay. Okay, so our area, when we add up values, is opposite, but our tangent slope, it's not really like flipping it. So our tangent slope is going to be the same. So if we've got, so this slope is not going to be the opposite because we're just finding the slope of the line and not the integral original y values. So we've got, if I go down, -2 over 1, so the slope would be -2, okay? F double prime of 0 is equal to F prime of 0. And at 0, there is a sharp point. So remember, sharp points are not differentiable. So does not exist. Okay. So on the first question, it says, on what subintervals from -4 to 6 is our original function increasing and decreasing? Justify your answer. So the rule is going to be the same. So f is increasing, and I'm going to leave it blank, when little f goes, is positive. Okay. And big F is decreasing when little f is negative. Now, if you want, you can write it like this, f prime. But you always want to relate your justification to what is given. So what's given is little f. So your rules on the free response questions need to incorporate what's given. Don't just say, oh, f prime is positive. You haven't really made that connection to the reader or the teacher that you know what f prime really means in terms of what's given. Okay? So on this answer, let's see, where is little f positive? So it was positive from 0 to 4. And we were negative from 4 to 6. And remember, when we go backwards, it's the opposite. Oops. Never mind. It's not the opposite because we're talking about f prime. So f prime, we are going to be going, it is positive until -2.5. So we are increasing from -2.5 to 0. And then decreasing from -4 to -2.5. Okay. All right, so if you want, I'm also going to make a sign chart of this. So this is little f, which is f prime. So we've got -6 to -4. We did -2.5. We did 0. And we did 4. So plus, plus, minus, minus. So decreasing, increasing, decreasing. Okay. All right, so what we want to do on part R is we want to find the absolute min and max. Remember, these include the endpoints. Now, we might, because we asked for both, I'm going to use the endpoints. If I only ask for max and min, we might be able to eliminate some of the endpoints that we show, but I'm going to go ahead and make a little table. And we need to include -4, -6, and I'll make another table. And then all of our possible extrema from our sign chart. So what I know is, keep in mind, if our original function was decreasing, then we increased and increased, and then we decreased. I need to consider my endpoints, and I need to consider -2.5. I don't have to consider 0 because I didn't change from increasing to decreasing. And then I also need to consider +4. And we want those original y values, okay? So that's the f of values. And then we're going to find the highest and lowest. So we've already done that up here. So f of -4 was h, so we said -2. f of -6, we didn't find. I'll find that later. -2.5, we didn't find, and f of 4, we did find, and that's 2 pi. Okay, so we need to find a few more. So f of, let's just do -6. So remember, if we're going backwards, because these are the original values, so use the signed integral areas. So I've got those canceled out. I thought we did find -6. Did we not? I guess not. Okay, so those cancel out. Oh, it's not -6. Oh, yeah, I do. Okay. What am I thinking of? That's so weird. Okay, anyway. So those two cancel out. So we had -3 plus 1 is -2. Oh, it's right there. Why do I have -6? That's not an endpoint. Okay, that's why, because I keep getting +6 and -6. So this needs to be a +6, because those are my endpoints. Okay, I knew it would take me a second. All right, so we did find f of 6. So 2 pi minus 2. So I need to do the -2.5, which was, oh, I will have to find that. So 1/2 base times the height is 2. So half of 2 is 1. So we've got -4. All right. So for our max and min, I'm going to go ahead and erase that. Okay. So our overall highest, well, that's 2 pi minus 2. I know 2 pi is bigger. So we have a max, so absolute max at x equals 4 of 2 pi. And because that is within the graph, we just have to state the rule. And we also show the others. So we would say because f of 4 equals 0, so it was a critical point, and f is positive to negative at x equals 4. Okay, so you have to say, we knew it was a possible local max and it was a critical point. We would say absolute min at, and let's find that. So let's see, 2 pi, so that would be like 6 minus 4, that's positive. So then right here, okay? And that wasn't an endpoint. So if it was an endpoint, then you would want to say something like it was decreasing up until that point. But we're right in the middle. So I'm going to say at x equals -2.5, and it's of -4 because little f of -2.5 equals 0, so it's critical. And f goes from, I always get this confused. We went from positive to negative. We went from negative to positive. Goes from negative to positive at x equals 2.5. So notice I named it and I kind of stated the rule, why it was a local. The table comparison, including my endpoints, does also further verify that it wasn't at the endpoint. All right, where are we concave up and down? So we're going to say f is concave up, f is concave down. And then the rule is going to be because f double prime, which is equal to f prime, is positive because concave up. Same thing here, because f double prime is negative. Okay. If you want, you can also talk about, or because the tangent slopes to F are negative. Okay, so one of these ideas. All right. I like the idea of saying the tangent slopes to little f are negative. That shows you can say both, honestly. And so you could do the same thing here. The tangent slopes to little f are positive. So let's find out, where was that? So our tangent slopes are positive. So concave up from 0 to 2. We've got negative from 2 to 6. And then we'll go backwards. Remember, you're going to use these signs though. So from 0 to -1, we have negative tangent slopes. Oops. From -1 to 2, there is no concavity. From -2 to 3, we have negative slopes. And then we had, oh, what am I doing? Oh, I'm going backwards. Oh my gosh. Sorry. These are positive. I can't read right to left. So those are positive from -3 to -2. I knew I'd catch myself. That's why I need to do it from left to right. 1, 2, 3. So from -4 to -3, those are negative. Whew, almost right with the final answer. I'm so sorry. I really should start at the left and go forward. That's what happens when I start in the middle. All right, so then if we sketch our function, we need all of those y values. So at this point, you're probably okay because I'm just going to go ahead and graph those. So I know I've got 0, 0. At 2, I go to pi. So 0, 0. At 2, we go to pi. I'm not going to be able to graph 1. At 4, we were at 2 pi. So at 4, we're at 2 pi, which is up. And then at 6, we were at -2. So what's that? 6.28 minus, so 4.28. So at 6, we're at 1, 2, 3, 4.28. Let's see, what would this one be? So 1/2 base times height. So subtract a half. So what's that? 6.28 minus 0.5, so about 5 point something. Okay. And then backwards at -1, we were at -1, -3, -3. So -1, -3, -3. But I need to find that one in the middle. So that was 1. So -4. And then -3. All right, so at 2.5, I'm at -4. And then f of -4 was -2. Okay, and then we apply our concavity. So I know this does take a while to do all these parts. Concave up from 0 to 2. And -3 to -2. Concave down from 2 to 6. 2 to 6. And -1 to 0. -4 to -3. And then do we have no concavity? Yep. So we'll just make that a line. Okay. And this would be F, the original. All right, so on your function, I tried not to ask you as many, but you got 10 questions, and then I have like a little application here for you to interpret. So go ahead and give that a try. I know this was a long lesson. There is a lot of information in here and notation. So I wanted to make sure I was pretty thorough and gave you a lot of examples.